We're trying to continue our work in Chapter 3. I spent the last hour before I got here grading papers for you, and I have some comments to make. Okay, first comment. I've indicated to you for documentation things like the mean and standard deviation. It's very simple. They're just 3 words you need to memorize, and I'm not sure why you didn't do it. That's the frustration. I want a formula, I want a substitution, and I want an answer. For the most part, the formula was ignored. It's not going to work, okay? If I tell you that I want documentation on homework and in a test, and you persevere and don't write formulas, you're going to lose points. It's a very simple issue. You have certain things you're supposed to do. It's simplest to do them rather than ignore them. That's simple. Now, in terms of doing the work, another basic kind of position you need to take. Get the work done. Okay? You have to put the time in. This is not a case where you can ignore problems, and I had a great many papers with problems undone. Give up sleep. Take fewer units. Don't work as many hours. I don't know what it takes, but this is not a case at this level where you can sandbag me. You'll find the consequence of it on the test. Okay? You've got to put the time in. You have to complete the problems. Okay? There were some outstanding papers, and a lot of you got fewer points than you expected. I took points off for not having documentation. I took points off for not having formulas, wrong answers. If you are going to give me a 5-number summary, you've got to give some defense, folks. Particularly if it's an odd-numbered question, I can read the answer book as well as you. Write out the numbers. Justify where you're getting Q1, Q3, the IQR, the median. Take the time. In the business community, we have a phrase, due diligence. Putting the time in, paying attention to detail, and make it work. So I wanted to get this set back to you by the end of this week because we have a 3rd set of problems now coming up. And again, let me indicate the time commitment you make in a class at this level. And I say at this level. This is a university transfer level course. Now, the only problems we tend to have with articulation is some universities don't think we go far enough. They want us to do one more chapter at the very end than we're able to do. And so, other than that, this level, we think in terms of an hour in class, 2 hours of homework. You've got 5 hours credit you get for this class, minimum 10 hours of homework a week minimum. And if you add the lab on top of that, I think it's realistic to think in terms of a 15-hour commitment per week for this class. Now I know that there are classes you can take in which you don't have to put in that kind of time. And I can't defend their practice. I can just tell you what it is in our department. And I've lived it. Okay, as an engineering major, when that was a kind of across-the-board expectation, taking 18 hours when you do chemistry, physics, calculus, English, a history or social science course, an engineering course, you were busy with school 24/7, 18-week semester. Okay? I don't think that everybody has to push themselves that way, but then take 12 units or take 6 units or whatever it takes. But you have a commitment, and that's what you need to do. And I push myself as hard as I expect you to. Okay? So I hope that the third chapter homework done over this weekend will look better than the second. The homework grade, as such, 50 points total of your grade, means that if we have 15 weeks, we're going to have about 150 points potentially that you could accrue. And then I divide the total you have by the maximum achieved. So if somebody gets 150 points, that will divide the total by. And I'll write that as a percent of 50. So this isn't destroying your grade, but it can mess it up. So if you get 20 points out of 50, and that's 10% of your grade, and that's about what it is, it can drop you a little bit. So I'm not talking so much about your grade as I am the commitment you're making and what you're trying to do with this course and what you're trying to get out of it. And I think the key here, and this is part of my motivation, this isn't just a prerequisite. Of all the things we teach in mathematics in this department or any college or university, this course has more practical applicability than any other course you can take. It has the greatest potential for influencing your future. We are at a point in this society where a BA doesn't get you much but beyond getting into an interview. Graduate work, master's degree work, doctoral programs, that's where the doors open. Those are going to be the life-changing kinds of events that you have an opportunity to do. And in graduate work, the STAT course is absolute. Don't sell your book. Keep it in your shelf. You will end up referencing it. Okay? Keep STAT graphics. You'll need it. And what we do in this course, you will come back and use time and time again. So put the time in, put the energy in, put the effort in. You can make it count for something more than a 5-unit course. And the Lord knows, I know how easy it is to forget the number of courses you've had and the content of those courses. At this point, when you've gone as far as you can go with the degrees, you have more units that you've forgotten than you're remembering. There are small little things that occasionally pop into your head, but it amazes me with a major in chemistry that I am totally feel out of my field when I look at a chem problem these days. Major requirements for the first 2-3 years of a chem major, and it's gone. Okay? However, for you, the STAT does become something you use in jobs, you use in research, so please, make a difference. Do something about it. There's time to turn it around. You've got to make the commitment. Now, just a reminder, we have Lab 3, histograms due today. And that is, I hope, going well. Are there any questions on the lab with histograms? Since it's due today and this is your last opportunity to ask questions about it? The lab work's going quite well. I'm very pleased with that. So that's the very positive part. The homework at the moment in a contrast is not so hot. Yesterday's lecture didn't go like I intended, but I hope it shook some cobwebs loose and you remember some things that you didn't remember very well yesterday. Now the question, what do we do with that normal density curve? What do we do with that transformation we made? We called it a z-score. So let me start with that, with the idea of a z. Okay? So we're going to write on the board, and that's for Jennifer's benefit so she knows where I'm going. I'm going to write the formula, and every time you use this calculation, I want to see the formula. So there's my formula. Now I indicated to you yesterday that the reason we are interested in this formula has to do with the fact that the empirical rule, my version of ER, okay, the empirical rule involves a very limited number of standard deviations. Okay, so we talk either in terms of here, in a theoretical sense, mu plus or minus k sigma, that's what I was talking about yesterday, the area under the curve. For k equal to 1, 2, and 3. And that's where we had the 68%, the 95%, and the 99.7%. Now this one right in here is a value that is of particular interest to us. And I'm going to disappear just for a moment as I bring up a page in the computer I want later. The 95%. If we say something has happened and it's significant, you may have heard a significant finding in research, a significant result. Or you hear the phrase, there is no significant difference. Okay. What we are saying in a kind of traditional role, that if it's significant, it would happen by chance 5% or less of the time. So this becomes part of a decision process. If something happened, and by chance it's less than 5% of the time, we would consider that a significant result. Okay? So with that in mind, this will be a very important value for us. But before we get into that, let me consider the notation I had yesterday. The N stands for normal. Remember I had a set of parentheses after it? And this set of parentheses has mu first, sigma second. And we, through this formula for z, argued that I can make a transformation. And that transformation went to this particular distribution. And I had a name for this distribution. I said it was standard normal. It was like getting that parabola in the standard form, y equals x squared. And the reason we wanted this is so we can use that table that was in the appendix that we looked at yesterday, table A z table. So I'm going to look at a problem that I often address from the standpoint an ideal world. If my exams were centered at 70%, remember my C's go down to 60 and go up to 79. So it's a very broad range. It has a lot to do with the way I grade. So I have a range of 20 points for my C's. The mid part of that would be 70. So if I had a test that I could write that would consistently give me a mean of 70%, I'd be pretty happy. Now what kind of standard deviation would I like? Well, if I had a standard deviation of 10 points, and I think of k equals 1, standard deviation on each side of the mean, I would have 68% of my grades between 60 and 80, correct? So 60%, 68% is in this interval, and I'll put it in an open interval for the moment, 60 to 80. And that's consistent with what I'm doing in my grading, right? So roughly 2/3 of my grades would be C's if I could write my exams this way. Just as information, I would have 95% of my grades between what? What interval? 50 to 90. Now, 50 is my lowest passing D, and 90 is my lowest passing getting an A, but that means I have 5% left to get an A or fail if I were to grade in the curve. And you've heard about grading on the curve. Okay. So this could define to some extent what the expectations would be for getting A's, that you're at 2.5% chance if this is the case. Now, if it's any solace to you, in the summer session, I had, I think, 10, 15, nearly 20% of the grades in one of the exams as an A. That was a highly unusual situation. So I don't force my grade distribution into grading on the curve. But this nonetheless, if I argue that my tests are written in this way, this gives you a sense of where the grades would be. Now, question. What is the percent of grades that might be between, well, let's say higher than 85? Percent of the grades higher than 85. Now I'm going to use the letter P for percent. But percent, we said in the pie chart, had another phrase going with it. Percent was what? Two-word phrase in the pie chart. That was the contrast with the bar chart. It was in the first discussion question in Lab 2. Nobody remembers. The phrase I'm wanting, relative frequency. Right? And then I tied that together with really probability. What's the probability, for example, that you'll get a country out of Africa drawing a country at random? Answer, roughly. Roughly 25%. Thank you, Nick. Roughly 25%. Probability, percent. Relative frequency. Sort of used interchangeably. So that little p could stand for probability. So what's the probability that a score on the test would be greater than or equal to 85? Now this doesn't fit nicely into my empirical rule, correct? Now I can show you on the graph where the value should be, and I expect that to be something that you can do. Okay, Erlinda, I'm going to ask you if you'll help me here. Will you get that straight edge over there, please? So I don't disappear in camera, and if you either throw it to me or hand it. Thank you very much. This is something I expect you to do. You're going to draw a bell-shaped curve, and then you're going to locate the center, and then you're going to locate where the curvature changes. Why is the point where the curvature change important? What happens there?
First standard deviation.
Again?
First standard deviation.
Okay. It's where the one standard deviation is defined graphically. So if this is mu plus 1 sigma. So if mu is 70, this is my 80, correct? So I can take that distance, replicate it over here, and this now is 90. So where should my 85 be? Halfway in between, correct? So I don't expect you to sit there and take a compass and bisect this line segment, but you can roughly estimate where the half is. That's not too hard to do. I'm going to draw an arrow there and say that's 85. Now, I'm asking for the area under this curve to the right of 85. That's what I'm asking. Now, I'm going to use Table A to do that. But I'm going to have to change my statement about x to a statement about z. So I'm going to rewrite this now as the probability that z is greater than or equal to a certain number. Now what you are seeing on the screen, if you look at just a monitor for a moment, this is the start of the documentation for the problem that you do like this. Replete with diagram. And may I remind you that your bell-shaped curve tails off left and right side of the axis without touching it. So you don't just draw a parabola coming down like the arch in St. Louis, although that's technically not a parabola. I believe that's a catenary, or as sometimes said by the English, a quaternary. Didn't even pronounce that well. I want this area. So I'm going to have to write a formula. And the formula that you're going to write is z, let's see, where do I want to write that? I guess right here. And I'll move over here. Z equals x minus mu over sigma. So I have that formula. And now I'm going to make my substitution. Remember, formula, substitution, and answer. So I substitute for x. My x is 85. My mean is 70. The standard deviation is 10. So z is equal to what?
1.5.
1.5. Agreed? 15 over 10? 1.5, which would be 1.5. Okay. So I'm going to take this 1.5 and I replace it up here. So now I have a statement relative to z. Now where am I going to find the area under the curve for a value of z? Your answer should be Table A. That's about page 680. Let's go there. So as I come back center, I'm going to go to that table that's on 684. Bring the camera down, turn the light on, and maybe. In fact, I want to be in 685, I guess, for the moment. Let's see if I can get this and then try to adjust the focus here. I'm getting a lot of glare from the light. Okay, now I have a light that will not cooperate. And now the focus. Okay, Jennifer. Now that's a 9332. Do we agree? Now I have just a moment. I'll try to show where that is. 9332, which is right here. That's where I'm looking if you're trying to find it. We got it? I don't want that number, but that's the number I see. Now what do you have to realize about that number? What does it represent? This is the crucial point. Everything to the left of the curve, yes. So I go to the top. If you have any doubts, I look at the top. Hope you like green and gold. Sort of matches your calculator colors. Okay, so 93.3% of my area is to the left of z equals 1.5. What can I do with that number? What? Subtract it from 1, right? So let me go back to the board. So we are saying that this is really equal to 1 minus the probability that z is less than or equal to 1.5. I know. It's hard to get all that on the screen. That's about as good as we're going to be able to do. Okay? Now you notice I use greater than or equal, less than or equal. There is no area at the point 1.5. So that's a rather arbitrary, whether you say greater than or equal or just greater than. The line doesn't create more area. So by substitution, this is going to be 1 minus 0.9332, which is what? In your head. I need a number.
0.778.
Good wrong answer. 1 digit off again. 0.0668. That's those digits. Okay. So 0.0668, or, as Orlando was saying, 0.067, 6.7%. Could we have done this in such a way that we avoided the subtraction? Remember yesterday I made a symmetry argument. Anybody want to take a shot at the symmetry argument?
Assumed it was 15 instead of 85.
No, I don't want to assume that x is different than what it is. That would be dangerous. You're right, but I don't want to go there. Nick?
Negative
Yes. The area to the right of 1.5, Nick said, is the same as the area to the left of negative 1.5. With me? That's what symmetry means. So back to the table. That's where I'm going. So I'm going to look for negative 1.5. Okay, I'm there, and it's in the green again, up to here. And there's my 0.0668. I get sloppy. I should have said decimal point. So 0.0668, roughly 6.7%. So how do I document that on what I did on the board as I go back to there? I wouldn't write this. What would I write instead? So I'm going to do what Nick was saying. I'm going to say that's the probability that Z is what? Not greater. What? Okay, less than or equal. I like that. I didn't hear one word that you may have said. I just didn't hear it. Negative. I heard the 1.5. I didn't know if I didn't get the negative part. Because that's where we are on the table, correct? By symmetry. But I need to know how you're thinking, what documentation you want to give. So if you go here, you're immediately at 0.668. And you don't do any subtraction. That's the neat part. Okay? Now I want to take this same problem and provide a slightly different question. So I'm going to, instead of asking what is the area to the right of 85, ask you this question. New question. Now nobody has particularly challenged me on the point, why would you ask questions like this? Who really cares? Now, the answer to that doesn't have much to do with x. It has a whole lot to do with x bar. X bar is that sample mean. And I'm going to go back to week 1. We had 18 means. And if I take a single sample, and you just get one mean, should I consider it unusual? Should it be occurring less than 5% of the time? So what I do is take that single mean and ask what's the probability of getting one that high or higher. So instead of an x, like I had as we slide over here just for a moment, I would have an x bar. The formula's changed slightly, and that's where we're headed. But I'm interested in how often an average occurs, not a single value. Now you, as a student, may be much more interested in what's my chance of getting a 95 or better instead of an 85. Okay, and that's 2.5 standard deviations to the right, and it's not very good if I'm grading on this curve. And again, I assure you, I do not resort back to this and determine your grades using z-values. Okay, and if half the class gets A's, I'm ecstatic because I finally found a way of communicating at the level I'd like. Okay? It would be a highly unusual event, and we would celebrate and expect it to occur again. Or I get upset. Let's go on. Back to here. New question. What's the probability that a test score would be between 85 and 65? Now, what would I do different than what I've done? And what would I do alike? What are the steps going to be? What kind of documentation would I want to see if this was a new question and you were starting it from fresh? What would you do? First step. You started out interestingly. You're going to take x less than the 65 and get that tail, and then take x greater than 95 and get that tail? We could do that. And then what are you going to do? Okay, I can find the z's. Then what will you do? Formula, okay, and then I look in the book, and now what am I going to do with those two numbers I have? You have two numbers you've managed to get. So far, you're okay. Sort of a backdoor approach. We could do it more directly, but you're right. Take a value to the left of 65, a value to the right of 85. Find those two areas, and my question, what do you do with those two numbers? Plug it back into what? Okay, we need help. You're up to the last crucial step. What has to be added to that description? Yes, you add up your two areas and subtract from one. That'll work. But it's a lot of work. Going to do a slightly different approach, but your approach will work. Now back to what steps do I want to see? First step that you should do at this point with the new question. Remember, this is like seeing it on a paper. First time, I've told you only, and I don't want Jennifer to pan over there for the moment, so we'll be okay. But just n is, okay, x is in 70, 10. So that's your information. That says x is normally distributed. And standard, yeah, I want to go there. So x is normally distributed, standard deviation of 10, mean of 70. Now, given that and this, and that's all you have in front of you, none of this is sitting there. First step you're going to do. A bell-shaped curve. Draw the picture. Remember the Kodak moment. You ought to be in pictures, digital or otherwise. So you want the picture. And you want to locate the values roughly in the appropriate region. So I am now, I hope, on camera 1 so that Jennifer can go to camera 2 so I can migrate across the room to the other board and take my ruler with me. And maybe an extra piece of chalk and one eraser. I feel like I'm packing for a trip. Okay, we go over here. And we're going to act like we are starting this over. So we start with a curve. Okay, critique. This curve relative to the curve I had in the front board is what? Well, I hope that's not skewed. How is it different? What? Flatter, right? Platokurtic instead of leptokurtic. I should have drawn them the same. I'm not going to try to redo it. A curve is a curve for the moment. Sounds like a line out of Elizabethan Shakespeare. A rose by any other names is sweet. Okay, a bell-shaped curve, as long as it looks like a bell-shaped curve, will do. This is going to be at mu at 70, agreed? Now, and this is not as easy to see as it is sometimes, I think, when I do them a little more leptokurtic. Where's my curvature change? Do you see it visually? Could you point it out if I ask you to come to the board, and I won't. But if I ask you to come to the board and point where that curvature changes, I hope you could do it. So as I look at it, it's somewhere about in there. Not very clear this time. And you might argue, quarter inch to the right or left. So without wishing to belabor the issue, somewhere about there. I'll just make the line wide. Now, what does that represent? What value? The 80, correct? Now, the minute I do that, I set up a metric. I can go ahead and take that distance and simply replicate it to the right and to the left and get my standard deviations. So I'm not sure those smudges look as good as tick marks, so I'll do the tick marks. Okay, this is a 90 here, this is a 60 here, and this is a 50 here, correct? So you could now very nicely locate 65 and 85, agreed? And I would expect you to do so. Now, it doesn't have to be terribly precise, but approximately. I mean, in the sense that somebody's going to argue with you very aggressively in this. There are my two values at 65 and 85. Notice I gave up the symmetry in this process. What region am I interested in? The area between, correct? So I could go ahead, feel like I'm now painting the wall. With gray tones. Would you want to live in a house with walls this color? I don't think so. That's the area I want, correct? Now, let's do it in a little different way. What was suggested was a valid solution. It was find the area to the left here, find the area to the right here, add those two together, subtract from one, and you're done. The picture will guide you. An alternative is to take the area to the left of 85, then take the area to the left of the 65, subtract, and you're done. The advantage of that is I can use the numbers in the table directly. So what I'm asking you to consider is that you will take the area to the left of 85, designated by the probability of x less than or equal to 85, that's percent under the curve, to the left of 85, and then subtract the area to the left of 65. And that would give me my result. True? I'm not getting quite the agreement I'd hoped for there. It is the statement I'm after. So this was the critical first step. Think of this as your second step. Third step is to find z. So I need to find a z for each of these. So up here, I'm going to write z. And what am I going to write before I do anything else? The formula. Good. And then I'm going to show substitution. So I'll do the 85 first. And so that gave me a z of 1.5. That's redundant. We did that already, correct? But then I'm going to do what? Again, I want the formula. Now, although I give you a page to write down information that you want to reference for the test, you get one page of notes, one side only, handwritten. I'd like you to know some of these formulas without having to write them down. And if you write the formula down every time you use it, there's a good chance you'll remember it. Okay? So this time I'm going to substitute in 65, subtract the 70, divide by the 10, and I get z is equal to minus 1/2, correct? Which you might prefer as 0.5, but I'll just do it as negative 0.5. So now I'm going to trade in this statement about x for a statement about z. So I'll just place one below the other and hope that that is comfortable to you. So this is z less than or equal to 1.5. And here I'm going to subtract off the probability that z is less than or equal to negative 0.5. A caution for some of you with your decimals. I found some interesting arithmetic oversights. I could call them errors, oversights, with tenths and hundredths, things like 0.2 times 0.2 is 0.4. How about 0.04? Or 4.6 minus 4.8 is negative 0.02 instead of just negative 0.2. Okay, so be really cautious with your decimals. You're getting some strange things that aren't going to give you correct answers from arithmetic errors. Now, if I go to Table A, page 685, you'll find here your 9332, correct? So I substitute. Now note, no symmetry this time. You have to look up on page 684 the negative 0.5. And would you allow me to look on your book with you, if you don't mind? Negative 0.5. And do you see in 3085? So I'm going to get 3085 with what? A decimal point. Now I'll do the subtraction, and I would suspect, looking at some of the work we're doing, it might be advantageous to have your calculator out at this point and get the number. Does someone want to share that value with me? I'd appreciate that. 6247? Okay, so 0.6247. That's the problem completed. Now, if you want to play the game of in the tails and then subtract, it'll work. You could use this number directly, because that would be a 3085, but then you'd have to do what? Find the area to the right of this. So instead of finding this value here, okay, you would have to use the negative 1.5 to get the symmetry argument for the 0.0668. So you take your 3085, your 0668, you'd add those two together, which gives you the 13, the 15, the 7, and the 3. And then I take that value and subtract it from 1, and I should get 0.6247. That was the original explanation provided, and it'll work. So this is an alternate form. But how would you have to change your documentation here? You'd have to say that you want 1 minus, then in parentheses, the sum of two values. So this would have to be written something like this. See if I can write it. 1 minus, in parentheses, the probability that x is less than or equal to 85, plus the probability, no, I didn't want to say that. I just screwed that up. I was not thinking clearly. That would be greater than or equal to 85, plus the probability that x is less than or equal to 65, which would be 1 minus the probability that z is greater than or equal to 1.5, parentheses, plus the probability that z is less than or equal to negative 0.5, which gives me the 1 minus the 0.0668 plus the 0.3085, and that does give me the 0.6247 that we were talking about. There's your documentation. I don't know if one seems easier than the other. My personal preference, biased as it is the one that we had to the left of this. But that will work. The picture is everything. Draw the picture, it'll guide you. If you try to do it without the picture, you have some really difficult times interpreting what you should do with the numbers. The picture is everything. Now let me ask you some questions from Table A, page 684, 685. These are important z values. Okay, I'm going to call them critical values. And they are going to be necessary for homework you do this weekend in Chapter 3. Critical values. Will you tell me the value of z that gives you 2.5% of the area in the curve to the left of the value? Translation. As I move over, Jennifer, and I didn't tell you I was moving. My apologies. Ah, there's a more leptokurtic version. Now, that is not as skewed as it looks on the television screen, because we are coming with a keystone effect from a camera that's making that look pretty sloppy. Now, I'm going to place here an area I'm interested in, and I wanted this to be 2.5%, so 0 to 5, correct? So I'm asking for the z value that does that. Do you find it in Table A, page either 684 or 685? If you look at the table and what area is represented, it should be clear to you that you're in 684. Somebody give me the number. I want the z, not the area. I've told you the area is 0.025. I want the z associated with that. Really? Negative 2.8, I think you've got a decimal off. I think you're looking at 0.0025. I want 0.025. Okay, good start. Good start. Negative 1.9. I need another digit. The 6. Do you see I'll have to go over to the column where the 6 is to see the 0.025? See, so far we've been doing single digits in the decimal. So there's a hundredths position. So if you're talking about negative 1.96, and I think this is document camera time, so let's go to the document camera for a moment. I see the negative 1.9, right? Now I need to slide over to a column that has a 6 in it. So I'm going to slide over, and remember your top of the green. Sounds like something in Ireland. The top of the green. Okay, this is low tech scrolling. You see the 0.25 in the green, top of the green, on the right of the screen. Okay, so I'm going to come over to there and right down to there. There we go. We got it? Now, as I bring this up, scrolling now, whether you think of that down or up is immaterial, there's a 6 up there, correct? So that says this is negative 1.96. So with that stated, this is called a critical value because it gives 2.5% in the left tail of the curve. Now over here, symmetrically, on the right tail is what? Another 0.025, and what can you tell me immediately by symmetry argument for z? This critical value is? Okay, positive what? 1.96. Okay, I'll buy that. Two tails involved, and the two tails cumulatively 5%. The magical 5 that gives you significance. Okay, the next one's a little bit harder. I don't want 2.5% here. I want 5%. Be careful. I want the 5% in this tail. You're going to have to play halvesies, I warn you now. Will you look at table A, page 684 again. I want 0.05 in this tail of the curve. But you're going to have to play halvesies. Okay. Very fast and very good. Give me the number again, please. And since you're on 685, I know you meant to say negative. Thank you. So negative 1.645. It's between negative 164 and negative 165. Split the difference. Do you see it? Okay, back to the document cam. Negative 1. Okay, I need to get over to the side. Okay, let's go there now, Jennifer. And then I'm going to drop down. There's my negative 1.6. 2 lines up in the green, correct? In the putting green. So we're going to come across. Now, let's see, I'll go right there. Now, at this point, I have to find where I am in the book. Okay, I'm in these two spots. This is too much and this is too little. Goldilocks and the Three Bears syndrome. This is over by what? 5/10,000ths. This is under by 5/10,000ths. So if I split the difference, I'd be right at 0.05. So these two values, as I slide up now, there was a 4 and a 5. Halfway in between is 0.045. That's called interpolation. And unfortunately, we don't do that much anymore because we have calculators, right? You may feel totally uncomfortable with it. But there was a time when we used tables for logs, for e to the x, the log base 10, square roots, and you had to make those kinds of adjustments. Now, relative to this, what could you say about 1.645? What does it give you? 5% where? To the right side of the value, correct? In one tail. Now we're going to have what we call one-tailed and two-tailed situations. And so the 196 and the 1645 are important values. Okay, the next one. This is the one I want to use in another problem related to your homework. 10% in the right tail. Okay, I'm low on the board. That probably means this is going to be Plato-Kurdi. But we'll see if I can do more justice. Not too shabby. Okay, there's my curve. And somewhere about in here, and this is just a rough approximation, but I want it to look bigger than the other values. I want 10% here. Okay, so you're going to be, technically, you could go to page 6845, 6845. That's giving you both pages at the same time, like 1645. Talk about being catatonic. Okay, on 684, you could find the negative number giving you what? 10% there, and then just give me the positive by symmetry. Or you can look at 685 and give me what? 90% in the table, because it'll be to the left of that value, and that'll give you your 10% to the right. Whatever the case, somebody hand me the number. Anybody? Nobody. Not yet. Keep looking. 10%. We need one of those little clocks. Tick, 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 tick. Or okay, I heard a value of 1.2. Then I heard an 8. Now, do we need this value here, or is it given just at 128? Let me go back to the document cam. Jennifer, just go to the document cam for a moment. Thank you. Let's see if the 128 is enough, or if we need to go a little bit further. Now, I'm going to go to the left part of the table because I can get the 10% there more directly. So I'm down to the negative 1, 2. That's at the very bottom of the screen. Flatten that out if I can just a little bit. Now I'm going to slide and try to keep that so it's the bottom line. Okay, there's a 1093, a 1075, a 1056, a 1038, a 1020, a 1003. So I'm right in between those two, correct? Typically, if you round off to the nearest thousandth, you're at 10%, agreed? And the other would be 0.099. So if we go to the nearest thousandth, what would be your value you would give me? Would it not be 128? And that will be the typical value we'll use. So we try to interpolate if we have halves involved, if we're right in the middle, but we don't try to interpolate if we're less subtle than that. So I think in terms of the nearest thousandth, it would be 0.100. We've got it. That gives you 10% in the tail of the curve. Now, if you're doing research and it's not to be published, and you're just trying to find a difference, and differences are hard to find, prototype development, we often use 10% for our level of significance rather than 5. If you're going to go worldwide in your publication, and you really want to be secure, we'll go to 1%, but that's for Monday. We've got 5, 2.5, and 10%. Now, what would I do with that value? Well, I'm going to ask you this question. What grade, remember we started with this in, okay, I'm on camera, 70-10, what value of X would give you 10% of the grades higher than that? So I'm asking you to basically answer this question where the area to the right of that is going to be 10%. Okay? Well, I can't find an X that'll do that, but I can find a Z, correct? I know that if Z is greater than or equal to 128, that's 10%. And then I ask you to consider a problem from beginning algebra. Here is a formula. You were given formulas like this. They weren't usually this esoteric. We did them what? With perimeters and areas and volumes, and then you had some letters and you were to solve for the other letter. What do I know here now that would allow me to solve for x? I know the z. It's 128. I don't know the x. I do know the mu. Do I know sigma? Yes, and we call that equation a what in algebra? Okay, it's a proportion. And what do you do with proportions to solve? There, very good. Cross multiply. And when we do that, we would say 10 times 1.28. So I'll say 10 times 1.28 is equal to 1 times x minus 70. So that says 12.8 is equal to x minus 70. So that says x is what? What? I heard it. I just wasn't loud enough. 82.8. Grid. We've got it. We answered our question. And you have a homework problem like that. And you have a lot of homework problems related to what we just did. The key is the picture. Documentation, and do what I did on the board. It's what I do in the study guide. And David Moore has a slightly different approach in the text that I don't think works as simplistically or as well. So please, refer to your notes. Okay, I'm down to nothing again. And I've run out of board, so that's about the right mix.